Today we will study about periodic table. In this we will be dealing with some of the periodic properties like atomic volume, atomic radius, ionization energy, electron affinity, density, etc. etc. First of all, we will know about what is periodicity. Periodicity is nothing but it's a gradual change in properties, either increment or decrement in the properties on going left to right in periodic table or going from top to bottom in a periodic table. Or we can say the repetition of the similar properties after a regular interval of time. Some of the periodic properties we will discussing. First of all, we will discuss about atomic volume. Now, when we see the trend of atomic volume in periodic table, first we will see in a period. In a period, on going left to right, first of all, the atomic volume decrease and then increases. Means the middle element is having the minimum atomic volume. While when we talk about atomic volume in a group, it increases continuously on going top to bottom. So we can say it has a regular trend in a group but does not have a regular trend in a period. Now why atomic volume is increasing continuously and going top to bottom in a group? It is because new shells are added on top to bottom, while in a period the electrons are added in the same shell. Second property which we will be discussing about is density. It varies with atomic number periodically. At first, in a period, density increases, becomes maximum in the middle element, and then decreases. This can be interpreted from the fact that it is opposite the atomic volume. While in a group, density is having very irregular trend. Iridium is having highest density. Next we will be discussing about atomic radii. Now there are different types of radii which we are going to discuss. One is covalent radii, second one is metallic radii, third one is van der Waals radii. What is covalent radii? It is half of the distance between the centers of nuclei of two similar atoms bonded via single covalent bond. Two atoms of nonmetals will be considering example a molecule of chlorine. In a molecule of chlorine there is a overlapping of the outermost orbitals of chlorine atoms. We are representing that like this. Let the atoms be A and B. So we will be taking the half of the internuclear distance between them, and that will be considered as atomic radii. Example, what will the covalent radii in this? It will be half AB will be equal to R, which will be representing as R covalent. So in this we are observing that there is a overlapping of the atoms of between the different atoms is generally present between the two atoms of non-metals. Second, we will be discussing about van der Waals radii. Now it is half of the internuclear distance between two adjacent atoms of the same element belonging to two nearest neighboring molecules of the same substance. Means what? That in the upper case we are considering the distance between the nuclei of two chlorine atoms. Now in this what we will consider is, let us consider the two different molecules of chlorine which can be said to be overlapped as follows. So what will be van der Waals radii? It will be the distance between the center of two different atoms or atoms of the different molecules. So we will represent this distance, let it be as E, this as A. So we will be representing this distance as R van der Waals, means van der Waals radii. So in this we can conclude that the distance of van der Waals radii will always be greater than Coulomb radii. Why? Because in this the distance is more than the overlapping, because in Coulomb radii we were observing that there was a overlapping of two atoms. In this the distance is more than overlapping. So we can conclude that the van der Waals radii will be greater than metallic radii. Third radii which we will be reading is metallic radii. As the name indicates, it's present between the two metallic atoms. Or it can be said as it is the half of the internuclear distance between two adjacent atoms in a metallic lattice. In this, there will be no overlapping of the atoms. Let me consider these atoms C and D, and this half of CD, what we'll call as metallic radius. So in this we conclude, we see that there is no overlapping and also there is no extra distance like van der Waals radius. So if you write the order of radius, it will be R van der Waals is greater than R metallic and greater than R Coulomb radius. Means the van der Waals radii is greater than metallic radii and Coulomb radii is the smallest among all the three radii. ये change करना है. We will see the trend of atomic radii in periodic table. It's very easy. What we'll consider is, on going left to right in a periodic table, the atomic radii will decrease, while on going top to bottom in a periodic table, atomic radii will increase. This is because first we'll consider the situation when on going left to right. On going left to right in a periodic table, the nuclear charge increased by 1. While the electrons are added into the same shell. While ongoing top to bottom in a periodic table, ongoing top to bottom in a periodic table, the number of shells increase, nuclear charge also increase, but the increment in number of shells per atomic size surpasses increment in nuclear charge. So we can say the increase in atomic radii on going top to bottom is tremendous. In case of transition metals, if you are considering the period ongoing from first to second period in transition metals, there is an increment in size from first to second, slight increment, but there is a very small change in atomic size ongoing second to third. This is due to the fact called as lanthanide contraction. Ongoing top to bottom in transition metals, the nuclear charge increase, but the shielding effect of d electrons is very less. Thus, there is less shielding effect and increment is in nuclear charge is always there. But here the nuclear charge increment is dominating the shielding effect very badly because shielding effect of d electrons is very less. If you write the order of shielding effect, it will be S is greater than P is greater than D is greater than F. Means the order of shielding effect is SPDF. Means the weakest shielding effect is seen in F electrons. A very weak shielding effect can be seen in D electrons. Thus, the nuclear charge is increasing on going top to bottom in a transition metal group. Shielding effect is going down. Thus, the atomic size tends to show a very less variation on going down the group. Otherwise, it would have shown like that in a normal group the atomic size increases, but in transition it is not so. While it is not observed, and this phenomenon is called as lanthanide contraction. The actual phenomenon of lanthanide contraction is due to the presence of F electrons. Because of lanthanides, in lanthanides we see that the last electron enters in F sub. And F electrons are having the weakest shielding effect. Thus the atomic size tends to be similar. From going down top to bottom. Well, if we are considering the atomic radii, which is having the smallest and which is the largest, alkali is having the largest atomic. Alkali is having the largest size, while the halogens are having the smallest size. Next property which we are dealing about is ionization energy. What is ionization energy? It is the minimum amount of energy required to remove an electron from an isolated neutral gaseous atom. Now if the electron is removed, so you can tell what thing will be formed, resulting in the formation of a positive ion. In this only we will discuss about various ionization energy. One is first ionization energy. It is the amount of energy required to it is the amount of energy which is required to take out the electron from a neutral atom. First we will take out the atom in a gaseous state, then we will apply I1 means the first ionization energy to it, resulting in the formation of cation, positive ion, which is singly charged because only we have removed only one electron. First one electron. Now this we have got as first ionization energy because only one electron is removed from the outer one cell and there is a formation of positive ion. Now second one is, now we are writing it as I2, m plus 2, yes. This ionization energy we are saying it as It is known as the second ionization energy because we are removing the electron from the singly charged positive ion. And the order of ionization energy is always like this: I3 is greater than I2, I is greater than I1. I3 is when the third ionization energy is when we remove the electron from the doubly charged positive ion. The order of energy of the successive ionization energies will be I3 is greater than I2 and I less than I. I3 is greater than I2 is greater than I. The reason being that it is always difficult to remove the electron from a positive charge ion than from a neutral atom. It is always much difficult to remove the electron from a positive charge ion, single positive charge ion, or doubly positive charge ion from a then when we compare it from a single positive charge ion. In simple words, removing electron from a highly charged species is difficult than removing the electron from the lower charged species or the neutral.